Thank you for attending my talk. I will present techniques related to color coding. So I will give a brief high-level overview of 3 color coding related techniques: divide and color, narrow sieves, and representative sets. There are many problems with best known algorithms rely on these techniques. And for example, directed k-path we will see here, undirected k-path on which you've already heard, the graph motif problem on which I think you will hear later today. And it is interesting to ask how much we can improve these algorithms, if we can improve them. And I've been studying mixtures of these techniques, so close to the end of the talk, I will present one result I obtained that relies on a mixture of divide and color and representative sets. Now, for historical reasons, I will say a few words about color coding. It led to the discovery of the first single exponential time algorithms for many subcases of subgraph isomorphism. So let's assume you solve such a subcase. Now, the problem when we solve such a subcase of subgraph isomorphism is to avoid repeating nodes. We cannot store the node set of every partial solution because there are too many options. Therefore, in color coding, we use a set of k color, and each node gets a color. The choice is random. Now, when we look at some specific solution to our problem, then with high probability, it will be colorful. Now, when it is colorful, it is easy to find it because we can just use dynamic programming. The point is that now we can store color sets, and there are only 2 to the power of k options and not node sets. We'll now see this in an example. So our example will be directed k-path for all of the techniques. In directed k-path, you have a directed graph G, and we ask if there is a directed simple path on k nodes. So here, assume that this is part of our graph and that k is 6. Now, each node gets a color. Here, for simplicity, let's assume that we use exactly k colors. Now, we want to get a colorful solution. So when we look at some solution, assuming that the solution exists, this is the probability that it will be colorful. Now, it's important to see here that this probability is high because we just want the solution to be colorful. It doesn't matter if the first node gets the color blue or green or red. It's only important that it doesn't get a color that a different node here in the solution also has. Okay, so this is why we have this probability and not 1 over k to the power of k. Now, a simple calculation shows you that if you perform this number of coloring iteration, then you will examine at least 1 iteration where the solution is colorful. Okay, and then in this iteration, we would like to find it. So let's look at such an iteration, and when the solution is colorful. Now, to find it, we can just use dynamic programming in a straightforward manner. We have entries of this form. In such an entry, we ask if there is a path on p nodes that ends at node V and uses the color set S. Now, what's important to see here is that we store color sets and not node sets. This is why in the running time you have here 2 to the power of k. Okay, because we only store color sets, and it is okay that we store color sets and not color multi-sets because we know that the solution is colorful, and of course we can ensure that we do not repeat nodes, that we get a simple path, because if a color is not repeated, then a node is not repeated. I also want to mention in the context of color coding that it can be randomized, and it can also handle weighted problems. Just instead of yes or no, you store here weights. Okay, so now let's move on. And in the past decade, 3 techniques improved upon color coding. First, divide and color allows to develop deterministic algorithms for weighted problems that are better than those based on color coding. Recently, powerful computation and representative sets allows developing faster such algorithms. The fastest algorithms, however, are based on narrow sieves, but they are randomized and are not well suited to handle weights. So let's start with divide and color. This can be viewed as a recursive application of color coding with only 2 colors. So let's see what exactly it means. So here in each step, we have a set A of n elements, and we seek a certain subset A star of k elements in A. Okay, A star is our solution. Now we color each element in A in one of 2 colors, say yellow and red, and now we have 2 new sub-problems. We need to find a certain subset of A star in the set of yellow elements, and the remaining elements of A star in the set of red elements. Let's see this in an example. So our example is directed k-path. And now assume that we don't only ask if there is a directed k-path, but for every pair of nodes v and u, we want to find a solution that starts at v and ends at u. Okay, so now we use the method and we color each node in red or blue. We will soon see exactly how we color the nodes, but our goal is that now assume that we examine an option where the first half of the solution of the k-path is red and the second half is blue. Okay, we will soon see how we get such a coloring. But assume we are in this situation. And now we have 2 simpler sub-problems. We need to find paths on k over 2 nodes in the subgraph induced by the red nodes, and paths on k over 2 nodes in the subgraph induced by the blue nodes. And you can see that if we know how to solve, if we have solutions to these sub-problems, then we can find k paths. For example, here we can combine these 2 solutions because there is an edge from W to R. And of course, there might be other solutions that we need to return if there is a solution that starts in a node other than V. And to solve its sub-problem, we can use additional recursive calls. Okay, so now let's see how we get the coloring that we want. So we need this definition. We say that a family of functions from 1 to n to 0, 1 is nk universal set if for every subset of indices of size k and a corresponding function f prime, there is a function in f that on I agrees with f prime. Okay, so this is exactly what we need, because we know that we will examine, we give to each node an index, and we know that we will examine a function here where the nodes in the first half of the solution will get 0, so we will give them the color red, and those in the second half of the solution will get 1, so we will give them the color blue. Okay, so there is a function that we will examine and will give us the desired coloring. And it is known that a small such family can be computed efficiently in time O star to the power of k, almost to the power of k. And this is the time we need for one step. Okay, next we will need to solve the sub-problems that we get and so on. So overall it can be shown that the time that we need is 4 to the power of k. Okay, now let's move to the narrow sieves technique. But before this, I want to say a few words about multilinear detection, the technique from which it evolved, because then it is easier to see the connection between color coding to multilinear detection to narrow sieves. So in multilinear detection, we associate a monomial with its potential solution. So instead of color sets, we have monomials. And we need to ensure that a potential solution is correct if and only if it is associated with a multilinear monomial. Okay, so instead of ensuring that a color is not repeated, we ensure that a variable is not repeated in the monomial. Okay, then essentially we look at the sum of these monomials and we reduce the problem to a different one where we check if a certain polynomial has a multilinear monomial of degree at most t, and then there's a known algorithm that solves it. Okay, it was given with the technique. Okay, so now let's see narrow sieves. So again, we associate monomials with potential solutions, but now we need to ensure that the correct solution is associated with a unique monomial, and that an incorrect solution is associated with an incorrect monomial that is associated with an incorrect solution is associated with an even number of such solutions. In other words, the set of incorrect solutions can be partitioned into pairs that have the same monomial. Okay, to make this work, we need to use a color set. Okay, and we need to ensure that our potential solutions, what we will call potential solutions, will be colorful. Now, some potential solutions are incorrect, and they will also be colorful, but we will be able to handle them by using this property. Okay? How do we ensure that we only look at colorful that the potential solutions are colorful? So here we use inclusion and exclusion, and we will soon see this in an example. And how do we handle the incorrect solution? So just look at their sum, and having a field of characteristic 2, they just vanish because of this property. So we end up with a problem of testing whether a certain polynomial is 0 or not, and this can be done efficiently using known tools, and here I mean that we get a randomized algorithm. Okay, so let's see an example. So we use a set of k colors, and we have a variable for every node and color, and a variable for every edge. And when we look at a solution, for example, then the monomial associated with this, we take the variables of the edges, okay, directed edges, and for each colored node, we have also a variable for example, if P were green, Q were blue, and U were green, we will have this monomial. And of course, if node is repeated, then each of its occurrences can get a different color. This is actually what we would like. We would like to look at the colorful potential solutions. Okay, so now we need this definition. So let Wx be the set of color walks on k nodes, avoiding colors from X. By walks, I mean that nodes can be repeated. And W colorful be the set of colorful walks on k nodes. So W colorful is the set of the potential solutions. Now let's look at the sum of the monomials corresponding to these potential solutions. Now we would like to evaluate this polynomial, but we do not want to store all of the color sets to ensure that we really look at colorful potential solutions. We do not want to store all of the color sets when we use, for example, dynamic programming. So here we can use inclusion and exclusion, and then you can see that in the inner sum we can just look at Wx, ensure that we avoid using colors from X, so we can have polynomial space. Okay, and here is 2 to the power of k because we are looking at every subset of C that contains k colors. Okay, so this is the time. Now let's take a closer look at this polynomial. So if we associated the monomials with potential solutions as we intended, then you see that the monomials of the incorrect solutions, they vanish because of this property. They are partitioned into pairs having the same monomials. Okay, and we use the field of characteristic 2. So this vanishes, and we end up with a problem testing whether a polynomial is 0 or not. Okay? So now let's just see a short explanation why we associated monomials with potential solutions like we intended to. So when you look at a monomial associated with the correct solution, then you can construct the solution from looking at the monomial. We know exactly which edges to use. Okay, here we use the variables of the edges, and we know exactly what is the color of each node in the solution. But when you look at incorrect solutions, okay, for example, here we look at the incorrect solution, then there is some node that is repeated. Look at its first and second occurrence and just swap their colors, and you get a different solution because it is colorful. Okay, so we got a different solution, but the monomial stays the same. We still have here, in this example, one XP green and one XP orange. Okay? So now let's move to representative sets. So this is the definition of representative set. We have a universe E of n elements, and let S be a family of subsets of size P of E. Now we say that a subfamily S hat of S K represents S if the following condition is satisfied. For every pair of disjoint sets X in S and Y whose size is at most K minus P, there is a set in S hat that is also disjoint from Y. So what does it mean? It means that if there is a partial solution in S that can be extended to a solution by adding some set Y, then there is also a partial solution in S hat that can be extended to a solution by adding the same set Y. So in a sense, we keep enough partial solutions in S hat so we can find the solution in the end. And we might also remove a lot of solutions, maybe, because we are looking here at a subset of S. Okay, so how do we usually use this definition? So suppose that we have a parameterized algorithm that is based on dynamic programming. Now, at each stage, this algorithm computes a family S of partial solutions. So what will we do? We just compute a family that represents it, and we replace every reference to S by a reference to the representative family. And by the definition of a representative family, the algorithm stays correct. And it might also be significantly faster because we are using now a subfamily that might be significantly smaller. So the question is, can we compute small representative families efficiently? So recently a powerful computation that answered this question was presented. Okay, and I will not give any details about this computation, but there is one thing that I want to say. So we will see the connection between color coding to divide in color and then to representative sets. Because in this computation, there's a certain data structure that is constructed, and when it is initialized by the computation that generalizes the computations of an NK universal set within the context of divide and color. Okay, so you can see that there are ideas from color coding and divide and color that are used here. Okay, so now we just use this as a black box, and we have an algorithm to solve a directed K-path that is based on standard dynamic programming. It means, for example, that we can compute families of this form, SVP, the node sets of directed paths on P nodes that end at V. However, these families can be very large. So what we really store are families that represent them. Now, by using the computation that I didn't show you the details, it can be shown that this is now what you actually store, the size of the families that you store. And overall, it can be shown that you get this running time. Okay. So I've been studying mixtures of this technique, and here I will only show you one mixture that relies on a combination of representative sets and divide and color in the context of directed K-path. Okay, so you can see that we get an improvement by using such a mixture. And also there can be other mixtures of these techniques that can lead to improvements for other problems. And I want to mention that this results also builds on a trade-off result that was obtained by these authors and also in a work I have with Dasha Chnai. So I will only give you the intuition that underlies this mixture. So let's assume that we have somehow obtained a coloring of the nodes such that if there is a solution that looks like this. Only and every ith node is blue. Okay, here in this example, I is 4. So we have 1, 2, 3 nodes that are red, then 1 blue, 1, 2, 3 red, 1 blue, and so on. Next, for simplicity, the illustration will show a solution like this. Okay, we don't see here the nodes and the edges, but you can imagine they are there. Okay, so if we want to use standard dynamic programming in representative sets as before, then you can see that the partial solution will look like this. This is the part of the path we already found, and white is what remains to be found. Okay, so in the illustration, this is a partial solution. Okay, so now assume that also we somehow obtain the partition of the blue part into dark blue and light blue. Okay, so that if there is a solution where the dark blue appears in the beginning of the solution and the light blue part appears in the end of the solution. Okay, at the end we will discuss how to obtain actually these red, blue, light blue, dark blue parts. Okay, so assume that we are in this situation. Now, how does it help us? So the obvious way is that when we are in the first half of the computation, then we do not need to ensure disjointness from the light blue part. Okay, we simply, at this point, we only use red nodes and dark blue nodes. So, of course, we do not use any light blue node. And this makes computations of representative sets faster. Now, when we are at the second half of the computation, now we are only adding red nodes and light blue nodes. So we do not need to ensure that we do not repeat dark blue nodes that we already used. We are only adding light blue nodes, so we can actually forget about all of the dark blue nodes that are in our partial solutions. So again, this makes computations of representative sets faster. However, this is not good enough because the time that we save in the computations of representative sets doesn't justify the time we will need to obtain the dark blue part and light blue part. So let's take a closer look at the worst time to compute representative sets. It's when we have a family of partial solutions that contain slightly more than half of the solution. When we are in this situation. However, when we look at each part separately, we see that the situation actually remains bad with respect to the red part. It contains slightly more than half of the red part, but it is actually good with respect to the dark blue and light blue part. It already contains all of the nodes in the dark blue part, so we can even forget about them, and it contains significantly less than half of the nodes of the light blue part. Okay, so we are good with respect to the dark blue and light blue part. So we give a more general definition of representative sets and the necessary computation that captures and that exploits this imbalance. Now, if we have the blue part, then obtaining the dark blue part and light blue part is not a problem because we just use one step of divide and color, just one standard step of these techniques, and we have the dark blue and light blue part. Now, obtaining the blue part is more problematic because we cannot really obtain a blue part that is as nice as I showed you in the illustrations. Okay, what we really do is we just obtain a blue part that contains the desired number of nodes, regardless of their location in the solution. So it means that if we look at the solution like this. So the blue part can be congested in different places, locations along the solution. And then we cannot use the idea that is related to the imbalance. So what we do is we use a procedure that implicitly cuts the solution into small directed paths and reorders it. So we get a solution that is relatively nice, but overall it allows us to use ideas very similar to the ones I told you, in case the solution is organized. Okay, so we can use the ideas related to the imbalance. Okay, so just to conclude the talk, so here I gave you a brief introduction to color coding related techniques. We saw 3 techniques: divide and color, representative sets, and narrow sieves. And at the end, I gave you just one example of how we can combine ideas from these techniques. Thank you.
Well, I have one. If you're combining the color coding and the multilinear detection, is there possibly an algebraic interpretation of what you're doing? Like some of the multilinear stuff involves evaluating over exotic ranges and so forth. Is there any possibility of
I'm not sure, but for example, already Andreas' algorithm for K-path, it is in a sense combines divide and color into it. And so already with narrow sieves, it was shown that divide and color is relevant. But, yeah.
Giannis? Did you want to comment on this?
There is a relation between divide and color or color coding. I don't know. I mean, color coding is a very special assignment, very restricted assignment. So you can view it as a very restricted assignment to the variables, which has a very low probability of success. And we view it as see it again as a bright assignment, but that's all I know. It's a restricted, very restricted assignment. And if you're using group algebras, ones I used, they would correspond to using 0, 1 vectors with only 1 in some position, dimension k. What I did was I used general vectors. Vectors can be arbitrary, but other than that.
And another question is, the multilinear detection technique, it doesn't give a natural witness structure. There's no easy way to get the witness structure. I'm wondering if the color coding can be used to speed up the discovery of the thing that's promised to exist.
So I think that actually it will be faster to use the multilinear detection, because then you can remove elements from the graph, for example, and actually find the solution at the end. So actually, I think that in practice, narrow sieves multilinear detection, if you're solving problems that do not have weights.
So maybe I have a question. Have you thought about actually getting an approximate counting algorithm using this combination of these techniques? Because I think for approximate counting, color coding is still
yes.
The best known algorithm, right? So one open problem would be to get a better approximate counting of k-paths.
Yeah, so this is a great open question. I didn't think about it.
Yeah, okay, sure.
Let's thank Meirav again for